Today we're going to talk about derivatives of inverse functions. Um, this particular topic is not terribly difficult. It can be confusing at times, though, so you have to be kind of meticulous with it. Um, and I'll be blunt. I don't think that this gets tested a lot on the AP exam. In fact, I think some years it doesn't get tested at all. I don't think I can't ever remember seeing a question on a free response that had this. Typically, it's asked as a multiple choice question, and if they ask it, it's usually one question. And so, um, in terms of being super important, for that, not terribly, but we can use it to help us with some other things later on. So this is the idea of derivatives of just inverse functions. So remember, two functions are inverses of each other if and only if their compositions yield x. That is, if f of g of x and g of f of x both give you x. So the thing I always think about is that they undo one another. So the notation also, my least favorite notation in all of mathematics is this, for the inverse of f, is writing f to the as a superscript -1. It pains me even to say it. I hate it. It's not the same thing as f of x being raised to the -1 power. They are not the same. And if you're like many people, you're like, well, if you don't like it, what would you have rather had? I would have rather that they had done f capital I for f inverse. That would be me. Now, you know, I wasn't at the meeting, and so, this is what happens when you don't invite me to the meetings. You you have bad outcomes. Anything would be better than this because it's confusing. All right, so one of the other interesting things about this is that if you have a point on one function with coordinates a, b, then on the graph of the inverse, it'll have the point BA. So the x and the y's are going to swap places. Probably when you first learned about inverses, you probably did, and I'm just guessing, but probably did some things where you just had a set of points and you reversed the order and graphed that, and that's the inverse. Okay? So that has the effect of making the graphs of f and g reflections of one another over the line y equals x. So if this is one function and this is its inverse, you should be able to fold it along this dotted line, hold it up to the light, and the two should match up. Okay? Now, why is that important? Well, let's think about this for just a second. Let's draw in the tangent line to y equals g of x at the point b, g of b. Why I decided to use b instead of a, I have no idea. So the tangent line would look something about like that, right? And the slope of the tangent line would be equal to g prime at b, right? Not a big deal. Now, if this graph goes to the point b, g of b, then there is a corresponding graph on the inverse that I'm calling f here, which has coordinates g of b, b, right? It's going to be the opposite order. If I draw its tangent line in at that point, it'll look something about like that. And the slope of that line will be f prime at g of b. Now, let's think about slope for a moment. Slope is the change in y over the change in x, right? If we have two functions that are inverses of each other, since the x and the y swap places, then this, instead of change in y over the change in x, what I can do is go, okay, for its inverse, I can switch that. That is, take the reciprocal of f prime of g of b. This would be equal to 1 over f prime of g of b. Because the x and the y exchange places, then in my slope, where this is in the numerator, when I go to the inverse, then this is going to be in the denominator. And likewise, I could do this one. I could say that this is equal to 1 over g prime at b. It works either direction. And if we take this one, although both of them can be useful, this is the derivative rule for inverse functions. It says that if f and g are inverses of each other, then g prime of b is equal to 1 over f prime of g of b. And you can get terribly, terribly, terribly mixed up in this. You have to keep in mind that in both of them, you're taking a derivative, but in one of them, it's the derivative of one function. The other one, it's the derivative of the inverse of that one. And what you're taking the derivative of also changes, and that's the part that students mess up on more than anything else. All right, so let's verify the derivative rule for inverse functions using f of x is equal to x squared, and that g of x is equal to the square root of x. So f prime at a, we already know what that's going to be, but let's pretend that we didn't know how to take the derivative of x squared for just a moment. This would be equal to 1 over g prime of f at a. Again, notice, if you go back to the other page, that is exactly what we have here, except I've switched the f and the g. But we can switch the f and the g because they're inverses of each other. It doesn't matter which direction we go. So, all right, this is going to be, well, what is f at a? Well, that's going to be a squared, right? And so I'm going to have g prime of x squared, or a squared rather, excuse me. And g prime, if I take the derivative of the square root of x, which is x to the 1/2, I'm going to have 1/2 of whatever's in here. And remember, a is a constant, so I don't have to use the chain rule here, to the negative 1/2. Well, 1 over 1/2 is 2, and a squared raised to the negative 1/2 power is a to the negative 1, so I've got 1 over a to the negative 1 is 2a, which is what we know is the derivative of f of x evaluated at a. Let's do it the other way. So let's find g prime at a. That's going to be 1 over f prime of g of a. So that's going to be 1 over f prime g of a is the square root of a. Using the rule that we know for the derivative of x squared, that's going to be equal to 1 over 2 times whatever this is, so 2 square root of a, which is 1/2 a to the negative 1/2, which is what the derivative of the square root of x would be. So here we just have verified that this does indeed work. All right, let's do some actual problems. Let f of x be equal to 4x cubed minus 2x plus 1, and let f inverse denote the inverse of f of x. Notice it doesn't say that f inverse is in fact a function. It is not. It is an inverse relation, not an inverse function. That doesn't usually come up in anything, but I think it's something you might think about at some point. So if I'm trying to find f inverse prime at 3, then what I want is 1 over f prime of f inverse at 3. So again, the way I remember it is that this outer function is the inverse of this, and then this next one in is whatever this function is, okay, that we have over here on the left. So first thing I need to figure out is, what is f inverse of 3? Well, what that means is it's the x value that's going to make f of x equal to 3. So I'm going to have 3 is equal to 4x cubed minus 2x plus 1. And typically, on the problems that you're going to be given, this is the sort of thing where you're not going to have a calculator, but you can kind of get it by inspection by just trying out some basic numbers. Almost always whole numbers. So like if I try 0, well, that doesn't work. If I try 1, I'll have 4 minus 2 is 2 plus 1. Oh, hey, look at that. X equals 1. So since f of 1 is equal to 3, f inverse of 3 is equal to 1. So this is going to be 1 over f prime at 1. So that's going to be 1 over, I'm going to go ahead and just take the derivative in general. That'll be 12x squared minus 2, evaluated at x equals 1. So that's going to be 1 over 12 minus 2 is 1/10. If it makes you more comfortable, and for some people it does, because it can get a little hairy with, the f inverse prime notation, what they'll do is the very beginning of the problem is something like this, let g of x be equal to f inverse of x. If that makes it more comfortable for you, great. Okay? The next two are very similar to problems that I have seen on multiple choice AP exam questions. So here, let f be the function defined by f of x is equal to x cubed minus x. By the way, if it was easy to find the inverse function, we would just find the inverse function and take its derivative. But think about if you had y equals x cubed minus x, reverse the variables and try and solve for y. I have no idea. I don't think it's a function. It's some odd relation of some kind. So if g of x is equal to f inverse of x and g of 0 equals 1, what's the value of g prime at 0? Okay, so g prime at 0 is going to be 1 over f prime of g of 0. Right? That's the basic derivative rule for inverse functions. So first we need to figure out what is g of 0. Well, it tells you right here, g of 0 is 1. So that's going to be 1 over f prime at 1. So that's going to be 1 over 3x squared minus 1 evaluated at x equals 1. So it's just a half. All right, last example on the next page. Tony, you look like you're thinking.
Why is g of 0 1? Isn't it g of 0 is 0?
So if you're finding, that's part of the reason that they did this is that if you substitute 1 into this, you get 0 out, and if you substitute 0 into this, you get 0 out, and that's why they specifically told you to use this. Okay? But yes, you're exactly right. This is more like the ones that I've seen more frequently, although again, I don't see these super frequently. Let g be a differentiable function such that g of 2 is 4, g of 4 is 3, g prime at 2 is 1/3, and g prime of 4 is 5. They're giving you more information than you actually need. They want to see if you can parse what is it that you actually need for this. The function h is differentiable, and h of x is equal to g inverse of x. What's the value of h prime at 4? Okay, so h prime at 4 is going to be equal to 1 over the derivative of its inverse, so g prime, not at 4, but at h of 4. So that's going to be 1 over g prime, and you're like, what is h of 4? Well, notice that g of 2 is equal to 4. If g of 2 is equal to 4, that means that h of 4 is equal to 2. So this is going to be 1 over g prime at 2. And g prime at 2 is 1/3. So it's 1 over 1/3 is 3. So if you can keep all of it straight, these are pretty easy problems, honestly. All right, I've got a worksheet for you for your assignment.